I have the difficult task to introduce quasicrystals to you, and it's a very mixed audience. There are experts knowing more than I of different topics, and there are graduate students which want to be introduced. Well, I will try my best. Let's start with a prehistory. 200 million years ago, quasicrystals formed, the first quasicrystal, and this has been found last year. So in Italy, a scientist in a museum studied a mineral called cateochite, and this mineral was found in Siberia, far away. And it was quite surprising that in this mineral there were small parts containing the elements aluminum, copper, iron, and these are elements forming one of the icosahedral quasicrystals. And you see here a TEM image of such an quasicrystalline inclusion, and this image looks like it should look for a quasicrystal. And this means, since this mineral was formed 200 million years ago, that quasicrystals can indeed be stable for such a long time. This is one of the questions, how quasicrystals are stabilized, more by entropy or more by energy or both together. And since at low temperatures, phase transformations to periodic structures are of course very, very sluggish, it takes a long time. And this at least tells us that quasicrystals seem to be pretty stable. We jump now to the 11th, 12th century, and there a guy was called Fibonacci, Leonardo da Pisa, and he was studying interesting problems of interest for merchants and so on, so everyday mathematics. And he had one of his problems was rabbits. If you have a pair of rabbits, put them into a barn or so and look after a year how many rabbits you will find. This was the kind of problems he was dealing with. And here you see this example. You start with a pair of rabbits, and after a month, this pair of rabbits had 2 kids, and after 1 month, the kids were grown up, could have kids again, and so on. And he counted how many rabbits after a certain period would be present. And he found a sequence of numbers now called Fibonacci numbers, and these numbers are quite closely connected with 5-fold symmetry, as we'll see later. These Fibonacci numbers can be expressed by these recurrence relations. So each Fibonacci number is the sum of the preceding 2 Fibonacci numbers. And it has one interesting property. If you have the ratio of 2 subsequent Fibonacci numbers, then the limit equals tau. Tau is the golden mean, and defined in this way. And it's also interesting to see if you have here the continued chain expansion of this number tau, it only contains once. And this means if you stop here this expansion, then you get an approximation of tau, and since you have only number ones, it has a very poor convergence. Yeah? For example, for square root of 2, it's much simpler. Then, beginning of 20th century, we have the discovery of the quasi-periodic functions. And quasi-periodic functions, simple way, can be defined like this. For example, you have a cosine and a second cosine wave, and here you have a factor a, which is an algebraic irrational number. And here you have, for example, such a quasi-periodic function in green, and here cosine function in purple. Beginning of 70s, Roger Penrose comes in, Sir Roger Penrose now, of course, and at that time he was interested in tilings of the plane. How can you tile the plane in an aperiodic way? It's very simple to do it periodically, but it's more sophisticated to find a way to do it aperiodically. And 74 he published a tiling which consisted of 6 unit tiles, and he needed some special shape of these tiles as a kind of matching rules. And if you put the tiles together following these matching rules, then you get quasi-periodic tilings. And this was popularized by Martin Gardner in Scientific American 1977. This was quite helpful. Here you see a later version of the Penrose tiling. The number of unit tiles you need was reduced to 2, fat and a skinny rhomb. And if you decorate these rhombs properly, then you can produce, for example, a pentagon tiling, or you can have larger tiles consisting of the smaller ones, and this is a hexagon boat star tiling. And all these tilings, you may think, can be used as kind of quasi-lattices for building structures. Well, and then Alan McKay, in the beginning of the 80s, he read Scientific American, and he got interested in looking whether these quasi-lattices, these Penrose tilings, would be what kind of diffraction pattern they would form. Yeah? If you have a periodic structure, you always get a diffraction pattern which shows sharp Bragg spots on a reciprocal lattice. And yeah, he tried what happens if he does an optical transform of such a Penrose tiling. This was the underlying Penrose tiling, and this is the diffraction pattern, and it clearly shows sharp Bragg spots and tenfold symmetry. So this was quite amazing for that time, because it was one of the dogmas of crystallography that only periodic lattices can have sharp Bragg spots. But this discovery by McKay, it was published in Physica, and it was overlooked more or less by most people. This was prehistory. Now we come to the history. And of course, history starts with Danny Shechtman and with his experiment of rapid solidification of an aluminum manganese alloy. By rapid solidification, cooling rate 1 million degrees per second, you produce amorphous metals. Yeah? You quench the liquid structure more or less in a ribbon. Yeah, and what he received was, again, if you look to these electron diffraction patterns in different orientations, you find here again a diffraction pattern showing sharp Bragg peaks and tenfold symmetry. In other directions, you have crystallographic symmetry. Well, and Danny, very young at this time, wrote in his logbook his observations, and here you see tenfold, and well, he was quite surprised by that. And of course, he told his discovery, for example, John Kahn, eminent metallurgist, and he was very excited, and well, this was the reply of John. Of course, he said, well, these are twins, go away. It took 2 years until this discovery could be published. It was published 1984 in November in Physref Letters, and it needed cooperation with Denis Gracias, which is here, for example. And well, and it's very carefully written, and the authors state here, for example, crystals cannot and do not exhibit the icosahedral point group symmetry. Yeah? So they had to repeat the crystallographic laws, and this means they had to say it cannot be a crystal. Yeah? And they a kind of icosahedral class model, a kind of random tiling model. Already 6 weeks later, paper by Steinhardt appeared, and Steinhardt knew the paper by Alan McKay. Yeah? So, and this made, of course, things easier, because then he had the connection to the Penrose tiling and had already the basis to develop a theory of how a quasi-periodic structure can produce this diffraction pattern with this point symmetry. So there was, for a year or 2 years, a heated debate between people who didn't believe in quasicrystals, said these are twins, and others, the newcomers, saying we have a new kind of matter, a new ordering state of matter. That's famous Linus Pauling, and he never believed in quasicrystals. Yeah? And he wrote a couple of papers, one, for example, here in Nature, where he says, crystallographers can now cease to worry that the validity of one of the accepted bases of their science has been questioned. So this is a very hard statement, and Pauling explained observations just by twinning models. Yeah? And since the quality of quasicrystals became better and better, diffraction spots sharper and sharper, he needed larger and larger unit cell to explain these observations by twinning models. Well, of course, there are twins known in this way, for example, but we can clearly distinguish between twins and quasi-periodic structures. Well, and indeed, the discovery of quasicrystals was a paradigm shift. And Thomas Kuhn wrote a nice book about that. And in this book is explained how it works. Yeah? If you have a scientific revolution, if you have completely new, the first thing is that you need, of course, the old paradigm to see that you have discovered something new which doesn't fit in this old paradigm. And this anomaly appears only against the background provided by the paradigm. And normal science prepares the way for its own change. And it was a paradigm change, and, well, it needed new scientists to develop this new science, and some of the old scientists, well, did never believe in that. Well, this was history, and what's now? Well, quasicrystals do exist. Quasicrystals are a new ordering state of matter. Quasicrystals can be stable. They are also metastable known. And quasicrystals can be grown like any other crystal, to centimeter size, for example. And here you see morphology of these icosahedral quasicrystals, which are pentagon dodecahedra. They may have triacontohedral shape. And here you have a quasicrystal with decagonal symmetry, tenfold symmetry. And that's a micropore. Yeah? You see here the scale, so it's a pore in a metal, and it nicely shows many, many facets with the overall icosahedral symmetry reflecting the symmetry of the quasicrystal. And here that's an intergrowth of a decagonal quasicrystal and an icosahedral quasicrystal, the system aluminium, manganese, palladium, for example. Now, what kind of quasicrystals do exist, have been found until now? And you can characterize quasicrystals according to their diffraction symmetry, symmetry of their diffraction pattern. And here you have the axial quasicrystal, so with one prominent axis, found so far 8-fold symmetry, 10-fold symmetry, 12-fold symmetry. And then you have quasicrystals with icosahedral symmetry. Yeah? And here you have Laue diagrams showing 5-fold symmetry, 3-fold, 2-fold symmetry in these different directions. We needed a new definition what a crystal is, because definition of a crystal was, before the discovery of quasicrystals, a three-dimensional translational periodic arrangement of structure, of atoms, structure motifs. And now this IOCR commission produced this kind of definition, So it was a definition not in direct space, saying it has to be periodic or quasi-periodic in this sense. It was a definition in reciprocal space, in a Fourier space. And to have a not too narrow definition, it was defined in the way that any solid having an essentially discrete diffraction diagram. You will see that the Bragg spots of a quasicrystal are densely distributed in reciprocal space. But the intensity differences between neighboring spots are extremely large, and therefore you see a discrete diffraction pattern, and therefore this fuzzy definition essentially discrete. Okay, and an aperiodic crystal doesn't have three-dimensional lattice periodicity. And here you see a diffraction pattern in general, or the Fourier spectrum in general, contains Bragg contribution and diffuse contribution. Here we have singular continuous, and here absolute continuous. And if the diffraction pattern of a solid, idealized solid, shows only Bragg spots, then it's a crystal. And if you have a three-dimensional periodicity, it's a regular crystal, a periodic crystal, otherwise an aperiodic one. And there are different kinds, not only quasicrystals, also incommensurately modulated structures and composite crystals. Well, quasicrystals are mainly intermetallic phases. And here you see the elements which can be part of a quasicrystal. All these yellow or red marked elements, and one of the red is needed in a quasicrystal. So quasicrystals are binary or ternary intermetallic compounds. But you see, most elements of the periodic table can be involved in quasicrystal form. Yeah, and here you see, in a schematic way, ternary phase diagrams. And here you see the stability ranges of the different quasicrystals. This is for decagonal, this is for icosahedral. And what I want to show with this is that some quasicrystals have very broad ranges of stability, broad in composition and also extended in temperature, for example. And others are just line compounds, very narrow composition range. And it's clear if you have a broad stability range, this means that you have chemical disorder. And this increases entropy and can stabilize the quasicrystal. But if you have a line compound, you cannot have this kind of chemical disorder. Then there are also soft quasicrystals known. And one example is shown here. These are dendrimers. So these are organic molecules, wedge-shaped here, and they self-assemble to micelles, as shown here. And as a function of temperature, you can produce a series of different structures. And in this example, you find at lower temperature quasicrystalline arrangement with 12-fold symmetry. Yeah? So you don't need necessarily atoms as building objects. You can also have micelles, as shown here. And Ron Lifshitz explains this behavior by the existence of two different length scales and three-body interactions. Yeah? So you have the different length scales are, you have very soft repulsion between the outer part of the micelles, and if you have too close contacts, you have a strong repulsion. This has been observed then also in polymers. So if you have three unmiscible polymers, as shown here, polyisoprene, polystyrene, and polyvinylpyridine, then you also form quasicrystals with 12-fold symmetry. And this has been explained that by minimization, of the contact area between these different polymers. So for non-metallic quasicrystals, 12-fold symmetry is symmetry of choice. And if you have just nanoparticles, here you have examples, nanoparticles of iron oxide and gold, or lead sulfide and palladium, and they mix them in a proper ratio, then you have a self-organized structure which shows dodecagonal symmetry. So this is quite amazing. You have quite different length scales, quite different potentials, and you always get these quasi-periodic arrangements. Then I don't say much about applications, because I personally don't see many important applications for the metallic quasicrystals, but there seem to be important applications for structures, for quasi-periodic structures, like for photonic or phononic quasicrystals. And what you see here is a structure, a quasi-periodic structure. It's a polymeric structure, and you got this quasi-periodic structure by direct laser writing into negative tone photoresist. And so this means you can create on micrometer scale, this is 4 micrometer, three-dimensional quasi-periodic arrangements. And if you send light through this photonic crystal, then you see, for example, here the diffraction pattern. It's quite a good quasi-periodic structure, and you can manipulate light with that, yeah? For example, for communication devices or computers, optical computers. So this and the number of publications for quasi-periodic photonic crystals is exponentially increasing. Now, approximately 15% of all publications on quasicrystals are dealing with this kind of photonic quasicrystals. And also phononic quasicrystals. So phononic crystals you use for manipulating elastic waves or sound. Yeah? And this is also scale independent. You can manipulate seismic waves with a wavelength of hundreds of meters, or ultrasound waves, or even phonons. Yeah? Phonons, this means for thermal protection, for example. And it works. Here you see, for example, such a phononic crystal made of steel balls in a polymer matrix, 1 millimeter diameter steel balls, yeah? Arranged in a quasi-periodic way, and then you get band gaps which are omnidirectional. And this is what's quite useful for such devices. How can we understand that quasicrystals form? It's really complex. Yeah? You don't have a repeat period. And first, let's look to periodic structures and to complex periodic structures. And we start with very simple ones. Yeah? So if you have objects, simple potentials, then you usually get dense packings. If you take now simple metals, copper, aluminum, and tantalum, for example, they have very simple structures, yeah? Like these apples or oranges, close packed here. And if you mix these three elements in a proper ratio, well, you get an intermetallic compound. And in this case, it's a so-called Laves phase. And, well, its complexity is quite reasonable if you compare it with the original materials. And you can describe it now by a packing of Frioff polyhedra. These are just truncated tetrahedra with some atoms capping the hexagon faces. So you go from simple dense packing of atoms, next step to a dense packing of clusters. And by cluster we mean just structural units. Well, now change the composition slightly, 0.4%, 5.7%, 6%. And what we obtain is much larger. That's a unit cell with almost 6,000 atoms. But just by changing slightly composition. Yeah? What changes? Electron ratio. That's it. Yeah? And we get such a complex structure. Well, how can we understand such a structure? We come later to that. Again, change composition slightly, and we get a structure with 23,000 atoms per unit cell. So simple elements, such a complex structure. Now let's replace tantalum by iron. We get a quasi-periodic structure. Yeah? Why? Simple elements. Before, complex periodic structure, now quasi-periodic structure. Well, the question is, why do such complex structures form? Why does nature do that? It could be much, much simpler. And how do the atoms know where their sites is? Well, let's crystallize such a complex compound. We start. This is the structure with almost 6,000 atoms. And if you start here, then we see that in the center of the unit cell, you have just a cluster free of polyhedra. It's just a part of the cubic Lavis phase, which also exists in this system. We let it grow, and then we add some clusters belonging to the hexagonal Lavis phase. So we have a modular approach. Nature uses a modular approach in this case. It grows and grows, still Lavis phase. And now there's another phase in the system aluminum, copper, tantalum, the so-called mu phase. It consists of these free of polyhedra and these hexagonal bipyramids. And they are also found here. And in addition, we get bifroster. So it's called bifrost. And these are the red ones. And then we have fullerenes. And we can see that the structure, these fullerenes come from the binary phase, aluminum tantalum. That's just a dense packing of these fullerenes, aluminum film. These fullerenes are not carbon, it's aluminum tantalum. And we can see here now, we also have these fullerenes. And we can go on. And that's a structure. And we see what we need is just best arrangement of some clusters, and each cluster is a given chemical composition which fluctuates around the mean value of this compound. But these clusters are not stable entities. Yeah? These are structural units because we can describe the same thing either as packing of these fullerenes and free of polyhedra, or in this way. So a cluster is just a way to better describe a structure, to identify the structural building elements. And some of these clusters may have, of course, different bonds inside than outside, but that's not always the case. Well, summarize this. All these compounds are found in the system aluminium, copper, tantalum, and modules of these neighboring compounds are used to build a huge structure. And now let's go to quasicrystals. Here we don't have a periodic lattice. We have a quasi-lattice, Penrose tiling, for example. And we can build a model structure just by decorating this quasi-lattice. atoms on the vertices in a proper size ratio. That's one important point. Quasicrystal need atoms to have a proper size ratio. And then we get, for example, a decagonal phase structure. And this is an electron density distribution in decagonal aluminium, nickel, cobalt. And then you can identify, again, clusters, 20 angstrom diameter. But you could also identify different kind of clusters. Here you see, for example, high resolution images, spherical aberration corrected, so very high resolution. And what you can see, some clusters decorating here these images, and you can really assign the atoms to the contrasts here. Interesting question is, for example, if you have a quasicrystal, how does the surface of a quasicrystal look like? Is it the same as in the bulk, or does it reconstruct? Is it different? And a lot of that has been done on quasicrystal surfaces, and fortunately, quasicrystal surfaces terminate like in the bulk. There are slight relaxations, but essentially the bulk structure exists. And this is also quite helpful if you want to determine a quasicrystal structure. Here, one example, again, aluminium, cobalt, nickel, and such a model cluster which fits quite nicely. If we go now to icosahedral quasicrystals, which are quasi-periodic in all three directions of space, then we find that we have basically three different types. And they are distinguished by their fundamental clusters. And we have here a shell structure of the cluster. And you see these two are quite similar here and here, but different here. And this is 55 atom Mackay cluster, 45 atom Bergman cluster, 75 atom Tsai cluster. So these are the building units, essentially, of all these icosahedral quasicrystals. You can describe them also by slightly different clusters, but this is quite useful. For example, here in the system aluminium, mangan, palladium, you have not only a quasicrystal, you have also an approximant. An approximant is a periodic structure which is built of the same clusters as the quasicrystal. And this is extremely helpful because structure analysis of a periodic structure is straightforward. And then you can identify a cluster and have a good starting point for the determination of the quasicrystal structure. Of course, you have some relaxations and atomic shifts, but basically this works quite well. So you don't have to look too carefully. These are just examples of how it looks like. It would take too long to explain everything in detail. So this is the periodic unit cell. And you find approximants which are larger and larger. And this means you can not only study the structure of a cluster, but you can also study how these clusters are connected. And this makes it easier to find models for quasicrystal structures. Here you have not a quasicrystal, you have the shells of the fundamental cluster, three different, and then you can decorate the unit tiles of the quasicrystal in this way and arrive to a structure model. Now, okay, 3D, we know 3D space very well. Now let's go to higher dimensional space. Quasicrystals can be described very nicely in higher dimensions. There are Bragg spots at the vertices of this lattice, and then you just project everything onto this line, and this line we call physical space. That's our space. And this direction is complementary space or perpendicular space. So this is outside of our space. And this is just for this single line, you need 2 dimensions. And since this diffraction pattern of an icosahedral quasicrystal is 3-dimensional, you need for all 3 dimensions 1 complementary. You have 6 dimensions to describe the quasicrystal properly. And now we come back to the Fibonacci sequence. We have seen Fibonacci numbers. And the Fibonacci sequence now is here introduced as a sequence of letters, L and S. You can assign these letters to the rabbits, large and a small rabbit. Or you can assign it to a structure, a long distance and a short distance. And if you start, for example, with this letter L, and you have a certain substitution rule, replace L by L and S, and replace S. And if you repeat this many times, you get a sequence which is quasi-periodic. And the number of L and S in this sequence are just Fibonacci numbers. And the limit goes then to the number of tau. And it's also interesting to look here. If you apply this substitution rule, nothing changes here. So this substitution rule leaves the sequence invariant. So you have here a scaling symmetry. That's also typical for many quasi-periodic structures, that you have scaling symmetry. You repeat the same motif on larger and larger scale. That's also valid for the structure, of course. And here you see a simple one-dimensional Fibonacci sequence, L, S, L, S. And then you see a scaled variant. Scaling factor is here tau. And you see that if you scale it, you don't create new vertices. It fits perfectly on the old sequence. Well, so this is example of a one-dimensional quasi-periodic sequence. And here you have the higher dimensional embedding. Again, that's a diffraction pattern which is one-dimensional in physical space and which can be seen as a projection of a two-dimensional lattice which is periodic. And the slope here of this lattice has something to do with tau. And if you have a projection in Fourier space, then you have a cut in direct space. Yeah? By Fourier transform, projection is related to a cut, and therefore you have here in direct space, in structure space, a lattice which is decorated by these line segments, and the physical space cuts the Fibonacci sequence out. So that's a secret between high dimensional embedding and quasi-periodic structures. We start with the diffraction pattern of a quasicrystal, embed it in higher dimensions, and then can derive the real structure. Then one further point is, do we have any relationship to a periodic structure? And we can now perform an oblique projection along these yellow stripes. And then you see you get this red marked average structure. In reciprocal space, this projection corresponds to a cut. So these reflections are periodically arranged. And this is the diffraction pattern of the periodic average structure. And what it could be used for example, if you ask how do Bloch waves propagate in a quasicrystal? Are Bloch waves quasi-periodic in a quasicrystal? Probably not. Yeah? But Bloch waves may only see the periodic average structure of a quasicrystal. Approximants in the higher dimensional descriptions can be achieved if you shear this higher dimensional lattice in a way that some vertices are brought to the physical space. It's difficult to see here, it's not enough contrast. Anyway, you can nicely derive approximants. High dimensional crystallography in general. It's long known since the 40s that certain symmetries which are not allowed in 3 dimensions are symmetries of higher dimensional lattices. And it's quite easy to derive by this Euler formula what dimension you need for compatibility of a rotation axis with a symmetry with a translational lattice. And here you see, for example, the dimension. Here you see which symmetries are allowed. For example, in 2 dimensions you have 3, 4, and 6-fold rotations which are in agreement with the symmetry of a periodic lattice. If you need 4 dimensions if you have 5, 8, 10, or 12-fold symmetry. And these are the symmetries found for quasicrystals so far. 6 dimensions for 7, 9, 14, and 18-fold. Recently, we found a colloidal quasicrystal with 9-fold symmetry. Other groups found one with 7-fold symmetry. So we have this case already realized now. That's just a diffraction pattern of a decagonal phase. I think if you idealize it, you see it better. You need 5 reciprocal basis vectors. And if you have these 5 vectors, then you have a Fourier module which corresponds to a C module of rank 4. And that's also a definition of a quasicrystal. If the rank of the Fourier module is larger than the dimension of the quasi-periodic pattern, then you have a quasi-periodic structure. Then you have a quasicrystal. You need at least 4 of these 5 vectors. Then one more property of a Penrose tiling is its scaling symmetry, as we have seen for the Fibonacci sequence. We have possibility to scale it, and you have here in black a Penrose tiling, and then in red a scaled, inflated, enlarged other Penrose tiling superposed, and here you can also define a kind of substitution rule for this scaling rule, and you can scale it further. So this is a new kind of symmetry which acts on such a quasi-periodic structure. And this is another kind of symmetry. It's pentagrammal symmetry. So the old pentagramma applies also to the symmetry of the Penrose tiling. And you see it's a kind of rotoscaling symmetry which applies to both the Penrose tiling and the Fourier spectrum of it. And again, you can also define a periodic average structure. So this was one point to ask, how close can a quasi-periodic structure be to a periodic one? And it's easy to answer for the Fibonacci chain. There you have a one-to-one imaging, one-to-one mapping of the Fibonacci sequence to a periodic structure. That's not possible for Penrose tiling, for example, but you get anyway a periodic average structure by this oblique projection. This is, by the way, a section through a 4-dimensional unit cell. This is a projection of the 4-dimensional unit cell upon physical space and upon perpendicular space. So you have to deal with higher dimensional unit cells and ways to visualize. And this is just a section, and these bars are sections through these pentagons. Yeah? And here you have the oblique projection for the periodic average structure. Now I skip it. This, you see the projected higher dimensional structure, and here you have the periodic average structure, and in red you have the quasi-periodic tiling. And you see that every vertex of the tiling is in one of the projected atomic surfaces of this higher dimensional description. Yeah? But you have cases where you don't have a vertex in it. So this gives you a measure how close a quasi-periodic structure is to a periodic one. So I skip now something. This is, for example, the periodic average structure of a real quasi-crystal, decagonal aluminium, cobalt, nickel, and this is a unit cell of the periodic average structure. And this is a way to image these higher dimensional objects which describe the quasi-periodic structure. This is the internal distribution of cobalt and aluminum and nickel atoms, and this is projected into physical space. Okay. This is quite useful if you want to understand the mechanism of phase transformation. For example, here you have a quasicrystal, decagonal quasicrystal, which transforms by electron ionization in a periodic simple structure. And that's a quasi-periodic structure, the diffraction pattern with these strong Bragg spots. That's in one direction. And this is the diffraction pattern of the transformation product. And you see the strong reflections on the same positions. And this means these strong reflections define this periodic average structure, and the atoms have only to move slightly to transform from one into the other phase. One example of octagonal tiling to please Shelomo. Well, here we have an octagonal quasi-periodic pattern, and here we have the different vertex configurations, and we mark these vertex configurations by colors, 6 different vertex configurations, and this is now in the higher dimensional description of the atomic surface. That's a tiling. That's now the higher dimensional object. And you see all these colored atoms form now some distribution here on this atomic surface, and we can partition in this way. So the information about this tiling is fully contained in this atomic surface. Yeah, you see how elegant this description is. That's now again the tiling, the atomic surface projected upon perp space. This is projection upon physical space, and that's again the cross section through the 4-dimensional unit cell. And you see how this is related. So I can go into details, just look at these nice colors and distributions, and how simple in high dimensional space everything gets. Again, that's now the periodic average structure. That's a tiling, and this in red are the projected octagonal atomic surfaces. And you see the octagonal tiling is very close to periodicity. Of course, not every vertex, not every projected atomic surface is occupied by a vertex, but every vertex is in such a projected atomic surface. So octagonal tilings are very nice tilings. So I have to skip this now. By the way, this is periodic average structure of an icosahedral tiling. That's aluminum, copper, iron. And here we have the periodic average structure. And this periodic average structure is very simple. It's sodium chloride structure. It's a face-centered cubic structure, and so it means that the quasi-periodic structure is very closely related to the structure of aluminum and copper, the main constituents of this tiling. So what I want to say with that is, on one hand we have these clusters and the way clusters pack. On the other hand, we have an underlying periodicity which may be important for the electronic waves. In all complex intermetallics, in all quasicrystals, you will find that the atoms are arranged on layers, flat layers, which are spaced quasi-periodically in all directions. And you always find this, and you find it also, for example, in this nice colloidal crystal. So this is an arrangement on curved surfaces. Again, also on these curved surfaces, all these lines play an important role. And this arrangement in atomic layers, together with this non-crystallographic symmetry and the cluster formation, is one of the, let's say, guides for the atoms to find their sites in the structure. Stabilization of quasicrystals. That's a difficult question because there are so many alternative structures which could also be formed instead of quasicrystals. But for intermetallic phases, basically electron concentration plays an important role. And this is on one hand the Hume-Rothery mechanism, so that you get a pseudo gap at the Fermi energy, or it's a kind of hybridization inside of clusters which stabilizes the quasicrystal. Again, both either orbital hybridization or Fermi surface Brillouin zone interaction. You may have both, and there are examples where you have the one thing and examples where you have the other thing. Let's go in details. So you can find either here the increased electron density around atoms which indicate more this, or you may have a pseudo gap which is clearly related to Fermi surface Brillouin zone interaction. And how to describe it in higher dimensional space? That's my last slide in this sequence. And if you have the Fibonacci chain again, and here you have the reciprocal space, then of course you can form in this periodic reciprocal lattice Brillouin zone. You can identify the first and the second Brillouin zone. And you can also define the Fermi sphere or Fermi circle in this case. And this means in direct space that you clearly have electronic wave related to the Fermi energy, to the wave vector Kf, and you have, of course, then here the periodic average structure, and it's one way to describe this Fermi surface Brillouin zone interaction in higher dimensional space. It works quite well. If you do it in physical space just, then you have your Jones zone. It's completely equivalent. So this is a higher dimensional description of this Jones zone approach. One of the last slides. Congratulations to ourselves. It was a good time. It was an exciting time. And it was thanks to Danny. But, of course, we also congratulate Danny.